Thanks for having me. I'll always come if somebody says I can speak. I wanted to start with an acknowledgement slide because if this is a PhD student workshop, I try to be simpler than at regular conferences. That typically means I run out of time because I start to really explain the details. And so let me first thank the people, and then we can stop at any moment when you have no interest in this anymore, you want food or something else. Okay, so I will highlight the individual PhD students and postdocs anyway, so the individual slides, but I definitely wanted to thank the 4 group leaders that were involved from our department in the work that I will be touching today. And of course, one always has to highlight where the money actually comes from, because this allows us to work. But now let's get started properly. The title was Machine Learning Accelerated Discovery of Materials. This is something that is super important at the moment because somehow we're running out of time. You see, I was in Vienna a few days ago and I saw this nice slide saying Das Verschwinden einer Jahreszeit at the Karlsplatz, a nice exhibition. So we're really warming up here. Snow is getting worse, and we're running out of time. So we have to do this fast. And the problem is that our traditional R&D cycles take decades, minimum 30, 40 years from somehow the kind of sandbox stuff that we do here up until something really hits a global market. And we can't do this anymore. And so many people nowadays dream up schemes like you see here when we want to find, for example, new materials that everything in the past was very slow and we don't like it anymore. And so somehow machine learning will solve this all, and you will see flowcharts like this, and they will have in particular buzzwords like this, like high throughput, because this will accelerate everything, and they will have other buzzwords like large data sizes, because in the end this is what machine learning very often needs. At least this is what many people believe. These schemes in principle can work, but they work under one thing that very often in these flow charts is only something at the very edge. Here you see it down here. It's called descriptors. What does that actually mean? So when we want to test a material, we're not really interested in a material just by itself. We want a functional material. We want it for some application. And I'll be talking about the energy conversion context. So we want a cool catalyst, we want a battery or something. So the material has to do a function for us. Whether this really is a material that is cool for this function means we have to explicitly test it, function testing. And that is typically very expensive and it takes a long time. In catalysis, we have to put something into a reactor. In a battery, we have to actually create the full battery cell and we have to cycle it. And because we are not just interested in one shot, sort of like, oh, it works for 10 seconds, but it needs to work for a longer time. We need to run many, many cycles in batteries. We need to run this for a really long time on stream of catalysis. And with sustainability becoming more and more important, we actually have to also somehow look into degradation phenomena. So we really want to have many cycles and we want to have this for a really long time on stream. All of this means low throughput because this is expensive and takes a long time. And this is why we typically, in these sorts of schemes, we don't evaluate the full function. What we instead do is we cheat. We evaluate what is called a descriptor. So descriptor is a quantity, can be anything, where we believe that it reflects the true function that we don't want to measure. But it's something that we can get quick. A super simple example, for example, in computational catalysis research is we have understood the Sabatier principle for about 100 years, and we know that we want certain reaction intermediates that we believe are important for a certain reaction to bind with an intermediate strength to the catalyst. Because if it binds too strongly, the whole thing is glued to the surface, nothing reacts anymore. If it doesn't bind at all, we can't get it activated. And so we want this with an intermediate strength, and then we, rather than really computing the full catalytic function, we just compute this absorption energy, for example, and then somehow postulate that whatever intermediate range could be, let's say between 1 and 1.3 electron volts, this is our target window. And then, yes, we can screen millions of materials because we just have to compute that one absorption energy principle. then these schemes work. The problem is, in particular in catalysis, and this is why I love your theme, taming complexity, it speaks from my heart, we don't have proper descriptors. We have tons of descriptors. I just named you one, an absorption, for example, but the problem is that all of these things are either bulk-like descriptors, and anybody who's in catalysis and knows that this is a surface phenomena will already wonder, if my entire descriptor that is supposed to reflect my catalytic function is only taking into account the bulk property of a material, how can it somehow really be characteristic for my catalysis? Or we have descriptors that are surface sensitive, but then we evaluate them for idealized surfaces. Computational catalysis, we, for example, love to do this with, if it's a metal catalyst, we love to do an FCC 111 surface, and then we put our adsorbates there and think, okay, this is a working catalyst. And then you can compute these adsorption energies. The problem is that by now we know that this is not the true thing. In catalysis, it's called working interfaces, and in batteries it's called solid electrolyte interfaces. What it basically means is that these interfaces that are in these energy conversion devices, be that catalyst, electrocatalyst, be that a battery, these interfaces are working, they're changing their geometric structure, they're changing their chemical composition, they're changing their morphology. And not just a bit, they're changing it drastically while they are working. So at the moment when we synthesize something and we think this is a cool material, what we basically at best achieve is that we synthesize and prepare a material that is a cool precursor for the true interface that will finally form when this beast is actually working. And then hopefully it's a cool interface. So we're basically really doing things very, very indirect. The problem is that we don't understand it. So sure, we can sometimes create a cool new catalyst, but it's a little bit more serendipity than really design. And this is why we need to tame complexity. It's not good enough to understand idealized single crystal surfaces. This is always a very, very good start. If we don't understand this, we're actually lost completely. But then we have to really understand surfaces that look like this. So this is supposed to be a copper nanoparticle on stream from micrograph from Robert Schlögel's department in our institute. Whatever it is, it looks more like something liquid. We don't have the resolution. This is supposed to be a rutile electrolyzer. Whatever this is not a rutile geometric structure that you're seeing here. Ingenious, creative chemists like Robert Schlögel immediately have super cool ideas what it could possibly be, so some sort of like clathrate kind of structures. But again, this is a little bit more wishful thinking than reality because we don't have the true characterization techniques actually to really nail down what these interfaces look like. And so before we can ramp up with these super cool machine learning, high throughput, screening, and accelerated discovery kind of schemes, we have to do our homework. And we have to understand these working interfaces. Then we understand them, maybe we can formulate cool descriptors, and then we can do this, but one step at a time. At the moment, we're not even able to understand the interfaces, and we definitely cannot formulate descriptors. Bummer. So we have to do our homework. We have to do things the classical way, the mechanistic understanding. We have to do what in principle, actually, most of us as scientists like to do much more anyways. Look into stuff in detail, try to understand it, get a mechanistic understanding, know where the atoms are, how things are actually moving. So how do we do this from a computational side? It's typically in these energy conversion schemes a multiscale endeavor because we have to somehow capture physics that takes place on many different length and time scales. The base, of course, for us in materials is always the electronic length and time scales because the electrons form the chemical bonds and this is all the music that we have. But at the end of the day, we have to really go up to a full macroscopic level because in a catalyst, for example, we could have or we likely have strong heat and mass transport limitation effects. And they, of course, occur on a true reactor scale and we're the latest in a macroscopic scale. And so in theory, we typically use electronic structure theory, so first principle techniques down here to really understand the elementary process at the atomistic level. Then we relatively quickly coarse grain this because this is sort of like looking into one process, but then there are many, many, many. Now we need to understand how they all interact with each other, and we go to statistical models here. We typically go going directly to lattice models. We give up the continuous degrees of freedom of where the atoms can actually be, and then we evaluate in catalysis. It's called a microkinetic model in batteries, some very similar sorts of things. Then we sort of like can get an intrinsic function, and then we very often include this into a macroscopic transport model, a continuum mechanics model, like computational fluid dynamics, for example. And the good news is, yes, we can do it. It's cool. This has been the work of an entire worldwide community, roughly 30 years it started ago, and we can do it. So this gap is closed. Conceptually, methodologically, we know what to do. We can do it. Spoiler alert, we can do it for very, very simple idealized systems. And if you've done it for one system, you don't want to do it again, because it's really, really complicated. It takes a long time. It can take you 10 years to do one system. So definitely not accelerated discovery. So in principle, we're a little bit lost, but here machine learning can actually help us. It cannot help us with the sort of like sales workflows with accelerated discovery, but you can use machine learning in many, many other respects. And so what has been happening in the last 10 years in this field is that machine learning in many different forms is now used to fuse into these classical modeling and simulation schemes at all different lengths and time scales. So you can put machine learning wherever you want to. This empowers this and then truly accelerates the simulation capabilities that at the moment we have. And I would like to, in particular, highlight one thing, which actually I would say in physical chemistry is about 80% of all machine learning that is currently done. And this is basically machine learning surrogate models. So this is the true machine learning technique that has now matured to a level that we really, it's no longer, oh, we need to demonstrate how cool machine learning is, but we can really get true value out of it and use it. And so just what is a machine learning surrogate model, also to bring a couple of things sort of like right, because very often people get very, very sketchy when it comes to machine learning. They equate it with miracles. and you know, in the end, even with machine learning, we drink and boil water. It's very, very down to earth. So a surrogate model is best explained if we understand what actually a physical model is. It's what we do normally. So a physical model, if you go to a very abstract level, has somehow some input. Then you have the actual physical model. Typically, we have this in the form of an equation. Think in terms of, for example, first principles calculations, the equation that we solve would be the Schrödinger equation. We do it typically in a computer, and it could even be a black box. This is why I draw it as a black box here. We don't actually need to know what my computer does. We feed somehow input into my computer or into our computer, for example, the atomic positions for the structure, the material that we actually want to calculate. The model, the physical model, solves the equation and gives me some system quantities, for example, total energy and forces that I want to have. This is what we, the simplest example would be also your pocket calculator. It's doing the same thing. This is expensive. Solving the Schrödinger equation for large systems is very expensive, and eventually we realize, well, we've done this somehow before. And you could say, in particular, oh, I did this structure file before, and I only moved my atom by half an angstrom to the left. Do I really need to do this calculation completely from scratch again? Because in principle, I've only changed something a little bit. And this is the idea of surrogate models. It's basically saying the workflow is exactly the same thing, but we're no longer solving the equation. What we instead do is we exploit similarity. So we have somehow a database of previous calculations of other things that we have already calculated with the physical model. And we use this to then be, in a sense, interpolate in a sophisticated way. That's it. A couple of things immediately fall out of this. First one is, if we have the perfect surrogate model, it will not be better than the actual physical model that we have trained it with. So if we, for example, train our surrogate model using DFT data, the best that my machine learning surrogate model will give me is DFT quality. I have all of the problems that I had with DFT before. I have it still, even though it's called machine learning. So, newsflash, there's still all the problems are still there. So the only thing that a surrogate model really gives us is speed. It's for example, machine learned force fields, to which I will switch in the next slide. They're roughly 3-4 orders of magnitude faster than a DFT calculation. Cool. I simply get 3-4 orders of magnitude in speed. But that's it. And I have not yet priced in the amount of time that I have spent to create the training data. So if my total time to create my training data is actually more expensive than I will ever use my surrogate model afterwards, I should start to question my actual approach to this whole thing. This sounds super easy, and I see a couple of people smiling. Read the current machine learning literature. You will drop dead laughing. Because this is what people do. They train forever and then evaluate the surrogate model 3 times. And then they want to publish a Nature paper. They can actually because it's machine learning. So very careful. So really down to earth, it's just similarity that we get, and it's just speed that we somehow get. Now, I will not tell you much about a specific form of machine learned surrogate model that I will dwell on, which is force fields, because I think, first of all, you have Georg sitting here. Knows a lot about this too, and you probably have heard talks from him too. And Ralf Strauss will give a talk Tuesday, I think. This will only be about machine learning force fields technology, so wait until then. At the end of the day, as I said, it can be a black box. What you want is basically a fast DFT calculation. So if you know what a DFT calculation can do, think of a machine learning force field, okay, just faster. What is more important, as I said, is this training. How much time do you want to spend on your training? And there are 2 ways to do it. The classical way, this is the 2010s. People were thinking, let's have huge databases. Let's have a worldwide community effort and put stuff together. This can work. We just got the Nobel Prize for it. It's called AlphaFold. So the entire community worldwide put their data together, and then they could train AlphaFold on top of it. This can work. In our field, this is, for example, now featuring under the name foundational machine learning models, Maze MP0 or so, for example, which are trained on the materials project. So again, gigantic databases. So the problem is they are gigantic databases, but the materials universe is more gigantic. So within every dimension of every single material and atomic position, and particularly if you want to go to interfaces, this is hilariously sparse. And so very often at the moment you can get at best something like a semi-quantitative accuracy out of foundational models, but this is getting faster. If you had listened to me 2 years ago, I would have ridiculed the idea to go for fixed large databases and foundational models, and would have said, oh, what idiots these people are. Now they're semi-quantitative, now I have to rephrase and have to admit, damn it, this development is fast. So maybe in 3, 4, 5 years or so, we will have foundational models that really do the trick generically, but at the moment they're semi-quantitative. So at the moment, at least, the moment or time being, people rather do what we call active learning. What does that mean? Rather than having a huge database and then somehow hoping that in this database, somehow the information and the similarity that I really want to have is contained, to then maybe find out that my specific systems that I'm interested in are sparse and I cannot really proper model it. What we instead do is we start with a very small data set. Can be stochastic, can be coming from chemical insight of the researcher involved. And then we basically start with a very, very crude first model, and we already use it, for example, for the simulation that we have in mind. And then what we need in an active learning model is some sort of like a feedback where the model says, I'm really interpolating no longer, I'm rather extrapolating heavily, and I'm lost. Don't trust me, please give me more data. This can, in the simplest case, be if you use a Gaussian process regression model, it's a Bayesian uncertainty that the model somehow has built in. But for example, in neural nets, the simplest thing is something like committee or ensemble approaches, where, for example, we initiate the same neural net training with different random numbers. And then we have 20 models, and we look at the variance of what they give us. And then if the variance is large, we know already, okay, now this thing is somehow lost and it's it needs more data. And this is how then, for example, in the simulation, you have a flag, oh, now I should actually have this structure calculated. So we query it, we put it to a DFT calculation, it's calculated, put to the training set. Typically do it batch-wise, so you collect a number of structures and data, and then you retrain your model, and you do this over and over and over again until you're happy and do it enough. And this is nice because it gives you very small data structures that you actually have to do. Very often you can get away with a couple of dozen data points. You don't need gigantic, materials projects, sort of like databases. And it's very agile. You can quickly get to this to start. But the problem is zero transferability. So this really only works for that simulation and for that system that you were interested in, because this is how it queried its own data and got better and better and better. If you take the same trained machine learning force field and then want to do it for another system, don't. It's really bad. So you have to do this again. So no transferability. But the nice thing is, if you really now mingle the actual simulation with the training, this makes it super, super efficient, because you really also get the feedback that wherever your simulation currently is, either the force field is trustworthy, or it flags it and says, give me more data, that in the end lets you sleep better at night. Good. A classic, for example, how do we do this? In catalysis, a bread and butter problem that we have is we have two compute reaction intermediates at the surface. I already told you, for example, about the Sabatier principle. We want to get a binding energy, for example. In this way, we need to know how these beasts actually adsorb at the surface. Now, if we only do CO adsorption, this is relatively straightforward to do because it doesn't really have many possibilities. But if we have larger reaction intermediates, finding the actual global minimum of what is the best adsorption structure is a pain in the neck. In the past, what we did was typically have a couple of local geometry optimizations. We did 3, 4, 5 different initial structures, maybe a monovalent, divalent, like bonding to the surface or a different site. We locally relaxed it, and whatever came out as the most stable, we said this is the global. This must be the right way. Now, of course, if we are 3, 4 orders of magnitude faster, we can do a global optimization. We can do basin hopping or replica exchange or really cool StatMech stuff. Huh? So finally, I can do StatMech. Here you see something how this works. So we wanted to do many reaction intermediates that are interested in the syngas context. And you see very quickly, so you see the different structures that this guy is actually taking. Very quickly, you see that we're, with very few training points that this thing actually queries, become super, super reliable. And it finds not only the right structure, but also finds whatever training data it needs for it. And this can be embarrassingly parallelized. You can have sort of like walkers running in parallel that explore these different sort of like structures in the global optimization technique. You can even, again, also here exploit similarity and diversity, because if there are several walkers that explore structures that are too similar, we kill one of them because they are not giving us any new information, and you can spawn a new walker with a completely new structure so that you really exploit and really explore many areas of your potential. Then you sort of like, this is all fully automatized. This is also, of course, what has come to be a standard in the last 5, 6, 7 years, is that we don't do things by hand anymore. Nobody sets up a structure file and then sends it to a queue. This is all fully automatized workflows. Unfortunately, very often too automatized, because sometimes I would like my students to look into the structure files and they would see some mistakes that they have done. But in general, you just send it off, and then the rest does it automatically. You get stuff in weeks that normally would have cost an entire PhD thesis. This is what you can do, but you see, this is again old school. This is a flat surface. And now let me finally get to my true topic. Like surfaces, working interfaces. How can we find those? And here, let me be really tutorial in bringing you into a technique called ab initio thermodynamics. How many of you know how ab initio thermodynamics works? It's good. It's a super simple technique, because the problem is, in DFT, we cannot compare structures that have different stoichiometries. So if we always have the same stoichiometry, then we can directly compare the total energy. Fine. Which one is the most stable? That's what has the lowest total energy is the most stable. But if we have different stoichiometries, problematic. And we can only compare it by saying, well, where did these new atoms and these new species actually come from, or where did they have to go to when we want to compare these two sorts of things. And in catalysis, for example, it would be the surrounding gas phase with my reactants providing reservoirs of new species. And ab initio thermodynamics does basically this. It's a grand canonical kind of technique. It evaluates then not the total energy, but the thermodynamic gives free energy, for example, or any other free energy. And it basically says if a new structure has 3 oxygen atoms more into it than another one, well, it says, okay, I needed to take these 3 oxygen atoms somewhere from a reservoir, that's my gas phase, and that has a chemical potential, and this way sort of like I can bring it in. It's basically like playing Lego. You want to build a house with 5 blue bricks and 7 green bricks, and if you want another green brick, you have to get it from somewhere, and this box is your gas phase reservoir. If that box is empty, it costs you an infinite amount of work to get a brick out of it, and this is where we say something has a chemical potential of minus infinity. If your box is hilariously full with green things, it's super easy to get a new one in, and you have a relatively high chemical potential. This is more or less what you need to know about ab initio thermodynamics. So there's always a chemical potential that relates somehow to the gas phase, which is your reservoir. So here we want to look into oxide formation on metals. And so the relevant gas phase reservoir is an oxygen gas phase around here. This is very little oxygen in the gas phase. This is a lot. And when you have a lot, eventually you will start to have your bulk oxides stable. And you can, for example, compute these surface free energies. And here is the problem of this. This is a super efficient technique, super nice, but it's politically nicely phrased, it's poor man's sampling, what we did in the last 20 years. What does it mean? We don't sample at all. We basically take a handful of structures that we want to compare explicitly, and from those 5 structures that we compared, the one that has the least surface free energy, we say this must be thermodynamically stable. And so how did we do it? Let's do a trip back into time. Mid-90s, I'm doing my diploma thesis. We're in the time when UH surface science rules. The Phil Woodruffs and Alec Bradshaws on this planet have just sort of like invented photoelectron diffraction. We have first STM images, and people hilariously think that a catalyst is something like an FCC metal, and it has a less than 1 monolayer coverage, for example, of oxygen on the surface. Some ordered adsorbate structures. This is what a working catalyst surface looks like. And so in those days, what we would have computed a surface free energy, for example, of a clean copper surface, and then one of these ordered adsorption structures that somebody in a diffraction technique or in an STM image had seen. For example, because this is a noble metal, here we would have only a very low oxygen coverage, so a P4x4 ordered structure. And you see now this has more oxygen inside, and this means that this surface energy will actually become smaller the more oxygen you have around, right? We have loads of oxygen in a gas phase, easy to take bricks from it, so stabilizing a structure that has lots of more oxygens inside will be easier. And you see that these lines cross, and so because we always believe that whatever we compare to the one that has the lowest surface free energy is the most stable one, this will be stable, we would conclude, my oxide formation, oxidation of the surface would look like here, I would have a clean surface, and then boop, suddenly I will have a certain coverage of oxygen on the surface. Time jump. Now we're in the 2000s. We're in the heydays when people realized that there's surface oxides. This is the time of Peter Wager, this is the time of Edwin Lundgren, this is the time of Herbert Over, and on the theory side, Phil Sauté, Georg Hesse when he was young, like me, for example. So now I'm already a postdoc. And these surface oxides are weird. And it takes much, much more time to actually characterize them. They're not just a simple adsorption structure on top of it. But you can do it. You typically have some incomplete information from experiment, and then you try out by hand different structures. This can be an entire postdoc. It takes a year to solve a structure like this. And for example, this is what this group work from Aloysius Soon's group. This is one of these surface oxides that can possibly form. So it's not simply an adsorption structure, but it is something that's sort of like has copper oxygen rings and somehow networks. Looks a little bit like a polymer on the surface. There are many different structural models that have been suggested, and for example, this 571. if you compute it, you get a much lower surface free energy here. And so suddenly we would revise our original prediction and say, no, 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 it's not just this little bit of oxygen. We suddenly can get much more oxygen on the surface. Cool. Now, the problem is what we have still done up to now is we have compared 5 structures. And these are all ordered. And these are only the ones that we found out because some experimental friend told us, oh, I've seen this in my lead image. It has this surface unit cell. And in my STM image, I see this blob. This could be an layer, something that looks like a parameter in the surface, etc. And so this is not good. So now we can finally sample because now we have a machine learned force field. And what we, for example, do here is that we do systematically more oxygen, more copper, and all the combinations of it. In each one of these huge 7x7 cells, we now do replica exchange molecular dynamics. Within no time, because we can suddenly have these energies and forces so quickly, we get basically more than 10,000 new metastable structures. In the past, we did 5. This is the nice thing of machine learned force fields in practice. You can't draw them anymore because it's now, you get so many lines, we basically only draw them as gray areas in here. And now we also have to rethink something that we did in initial thermodynamics for the last 20 years. We always just declared the lowest one, this must be more stable. But if all of my structures have surface free energies that are very, very close to each other, basically within kT, they're degenerate. At a finite temperature, they can, of course, all be present at the surface. And so we can now resolve a long-standing mystery because this is unphysical. These jumps in the coverage that we got in the past are wrong because it means I'm changing my pressure by an infinitesimal amount and suddenly, boom, I get much, much higher surface coverage. That makes no sense. In physics, we don't have just abrupt changes. So we have something more like this now, because we now Boltzmann average in here. We can actually find some new structures. They're just different combinations of these 5-7 rings. But more importantly, there are many, many structures in here that are disordered. And they're only really a little bit less stable than those few ordered ones. Which of course makes sense because in the experiment, they spent months to see that one small domain that is nicely ordered. And that's the STM image that they put in the publication, and they don't say anything about the 97% of the surface that looks like shit, and that they really just say this one. But a true working surface is disordered. We have to get out of the crystalline comfort zone. It's just because we had the characterization techniques and the computational techniques that only work with order does not mean that order is what is relevant for our applications. In catalysis, disorder is key, it rules. And so finally now we have really a systematic way of how we can address disordered surfaces. And of course it makes no sense to just say this one surface structure anymore. We have to consider entire ensembles and we have to average over these ensembles whatever properties we have. For example, an absorption energy of a reaction intermediate. It has to be an ensemble average on all these sorts of things. But now we finally have a key to it. And that is a huge step. And maybe, as I maybe expected, I basically showed you 10% of what I showed today. But I think it's sometimes better to, in a PhD workshop, to do some things very simple. Because what I really hate with machine learning, I really hate machine learning, trust me, even though my entire group does it now, is that all the people are just telling you, oh, this will solve everything and will this disruptive changes. Nobody tells you what it actually does. So here, you have a very concrete example. It's not rocket science. It gives what machine learning gives us here, and you will hear the technical details from Ralph on Tuesday, is we can get a DFT calculation 3 to 4 orders of magnitude faster than we can. This is not much. If you actually think in terms of Moore's law, they have just given us the computers we would have gotten in 7 years anyways. But nevertheless, it's cool to have these computers, right? And you here see a practical realization simply because we can do 4 orders of magnitude faster calculations, we can finally sample, and now we can open the door to really address disordered surfaces and become real and get out of this low temperature UHB surface science that we have really worked on for the last 40 years, which in catalysis it's a cool first insight, but it's not the reality. So with that, I think I'll stop it here. I would have tons of other stuff, but maybe it's good to have this one thing in too many. Thank you.